So today, what I'm going to do, so my task is to be more of an introduction. So my idea is to provide an overview for people that are, have little or no knowledge about agent-based modeling, so where it comes from and where we are now, and somehow pave the way for the other speakers. Before starting, I think it's appropriate to acknowledge Malcolm Russell Jr., who passed away recently. He was one of the pioneers in complexity economics, and his contribution cannot be overstated. So he was a great author, in particular bringing his analytical skills. He was son of a mathematician and a good mathematician himself, to the study of complexity, the introduction of complexity in economics. He was an enthusiastic and patient mentor for many students and many younger people that were approaching this field, including myself. And not last, he contributed to popularize the approach by being editor of generalist journals in economics and macroeconomics. So making, without compromising the standards, making the approach more popular among economists. So I will start from far back in time. So the idea is that in talking about complexity in economics, I think it's good to go back from where the current approach to economics started. Economics started more as a social science, more as a political economy, with a political economy approach. And then with the idea of becoming quantitative science, economics took as a model the king or the queen for science. At the time, that was physics. So the approach that was introduced by Barras first was basically modeled on what was at the time the statistical physics, which was based at the time on a reductionist approach, so the classical Newtonian physics. The classical Newtonian physics was abandoned in the 20th century, while economics, in particular macro, so I will mostly talk about macroeconomics. Macro has retained this sort of reductionist approach, so the approach that underpins current macroeconomics is still the reductionist approach, of course, with a number of developments and barriers. So I guess most of the people here may be familiar with the current approach in economics and in macro in particular, so I thought it would be a good idea to compare the approach of complexity economics to the approach of the standard macro, so the DSG. So in complexity approach to economics, we have that agents are normally not fully rational, so they are unable to make complex decisions, in particular to achieve an intertemporal optimization over an infinite horizon for a number of reasons that we are going to see. And they are typically heterogeneous, so can be full heterogeneity among agents. So the economy is never really in equilibrium, so the idea that the economy is in equilibrium is then hit by an external shock that somehow makes the economy away from this equilibrium is foreign to the complexity approach. So the complexity approach, we have a continuous evolution of the system, so the dynamics is what is important, and these dynamics can be nonlinear, and equilibrium is only one of the possible outcomes, not more likely than any other, among all the possible paths of evolution of the system. So the main object of studying economics from a complexity point of view is understanding how agents that have a limited vision of the system interact and generate what we will see, what we will define later as the aggregate outcomes. So there's the idea of efficiency, again, is impossible to study, while is the focus of standard math. So let's start. So I'm going to talk a little bit about complexity in economics, because agent-based modeling is, as we will see, the way of modeling, of introduce complexity modeling into economics. So I think it's a good idea to start really with the theory and then see how this theory is declining in practice in economics and in macroeconomics. So there are a number of definitions of complexity and complex systems. So here, this is mine, basically by taking pieces and bits from other definitions. So let's define the complex system as a system that is composed of parts or subparts, so there can be different levels of aggregation. These parts and subparts interact among themselves directly and indirectly through the environment. And this interaction, dynamically over time, gives rise to what we call emergent properties or emergent behavior. So let's examine one at a time the elements of this definition. So first of all, we have different parts of subparts. So heterogeneity and interactions are the building block or the main characteristics of a complex system. So agents are heterogeneous under different points of view. Being heterogeneous, the interaction is interesting because, of course, agents, as we will see, they'll evolve and the interaction being heterogeneous can generate interesting dynamics. And these interactions also implies the existence of a network. Network can be complete, incomplete, and normally, as we will see, agents focus on their portion of the network, so on a subset of nodes or a subset of agents that they can see from their point of view. Given this condition, full rationality is hard or unlikely to observe because, of course, agents don't know the evolution of the system. The evolution of the system is endogenous. So the best that they can do is to have some heuristic rules that allow them to adjust and adapt to an evolving system. This interaction generates emergent properties. And emergent properties, the main characteristic is that they cannot be inferred from individual agents. So even studying the individual behavior of one or more agents, given the interactions and given the network that exists among them, we cannot automatically infer what's happening at the aggregate level. So this is, if you want, the main point of departure from a reductionist approach in which we have that we can understand the macro from the micro. Finally, maybe more interesting, we have an evolutionary dynamic. So we have strong path dependency, which is due to the interaction of agents, and time matters, meaning that we have a dynamics that is not reversible. And this dynamics is due to the evolution not only of the system, but also of the single agent. We have a dynamics also at the individual level or at different levels of aggregation, in which some agents are selected, meaning that some agents survive through the dynamic evolution of the system, some other agents cannot survive. The agents that survive retain the characteristics that allow them to survive and innovate those characteristics that are less fit for the new system, for how the system basically will look like after the interaction. So we don't have Nash equilibria, or we cannot have, or again, Nash equilibria can be a particular outcome, but we have what we can define as an open-ended state of space. So the state of spaces cannot be limited, so we have an infinite possible outcomes, and there's not a point in which the system stops evolving, unless in very particular. So now let's try to be a little bit more formal, introduce the notion of self-organized to introduce the notion of self-organized criticality, we refer to what we can call a fractal structure. So a system in which every subset of results display the same statistical characteristics, so we are talking about now probabilistic terms of the whole system. And I'm going to be more precise, or let's say less formal in a moment. So the fractal structure implies that extreme events, so events that completely change the system, change the system to a large extent, are not unlikely. So there is the possibility of transformation of the system that are high order. These transitions are the result of what Perbach some years ago defined as self-organized criticality. So the system is spontaneously organized. Spontaneously means that this type of organization is the result of the interaction of the components of the system, organize itself in a situation that is critical. Critical meaning that is prone to changes. So this system is in a situation in which a small shock can generate a larger phase transition, so a transition to a different shape of the system. And this phase transition, so the magnitude of this phase transition, will display a fractal structure. So if we observe this type of phenomena, we are in the presence of self-organized criticality. So let's look at a very, I think, intuitive example, which is the example of the sand pile. So let's imagine that we drop, so of course, computer simulation, we drop a grain of sand at regular intervals at each point in time. And this continuous action will generate at some stage a sand pile, so a pile. And if we continue dropping grains of sand, we will observe phase transition, meaning we will observe an avalanche or more avalanches. And these avalanches will occur at the irregular point in time and also will have a different magnitude. So there will be smaller, larger change of the shape of the sand pile, despite the fact that the shock is always the same. So the shock is always a grain of sand dropping every second or every regular time. So the events, we are going to observe in the sense that the shape of the different avalanches, so the different phase transitions, will look like a fractal. To be more precise, to introduce some more formal probabilistic terms, the size of the avalanches will be a power law. The power law looks like equation 1, in which we have only two parameters. One is x0, which is the minimum size of the event in the distribution, and alpha, which is a positive. What is particular about this distribution? That this distribution is scale invariant. So if we take log of both sides of the distribution, we have a linear function. A linear function means that the proportion of events larger than x1 follows the same rule. So wherever we are in the distribution, the ratio between the size of two events is the same because of the probability, of probability of two events, the ratio of the probability of two events is the same. This is due to the fact that operating a logarithmic transformation, we are in the presence of a linear function, which means that, again, extreme events are not unlikely, but they follow the same decay as smaller events. And according to Bach, the emergence of a power law distribution is the sign that we are in the presence of self-organized criticality. So of a system in which phase transitions have a fractal structure in which small events, small external shocks can generate large events with a probability that is not different from the probability mechanism that generates small event, small phase transition. So is the economic system complex? Intuitively, is an appealing idea because the economy is composed by a number of heterogeneous agents, firms, households, policymakers, and so on, and they interact with the limited vision what's going to be the future. So let's say in terms of the formal definition, the approximation complex system, the model of a complex system of the economy as a complex system doesn't seem too far-fetched. But let's see if we have some evidence to ground this approach. So the first piece of evidence is the ubiquitous presence of power law distributions in economics and in finance. We have power law distributions, we have fat-tail distributions. So we have distributions in which extreme events or the presence of very large agents, firms, or households cannot be excluded. And then we have a literature that basically is rooted in evolutionary economics that studied the evolution of the economy, and in particular the evolution of technological progress for firms, and found that this the process of evolution is not a regular process, can be linked, for example, to R&D expenditure, or can occur at a regular intervals, and is also not transmitted in a predictable way. So evolutionary economics provide, since basically Nelson and Winter in the 80s, an interesting support to the idea that the reductionist approach doesn't really work for economics, or let's say can be an oversimplification that focuses on one particular outcome, which is the equilibrium, instead of multiple possible outcomes. So this is more the theory. So let's now be a little bit more practical. So how can we model complexity in economics? So started from the 90s, some researchers started implementing agent-based modeling in economics as a way to treat the economy as a complex. So here I have a definition that I took from the website of latest fashion. So the idea is that agent-based computational economics, computational is a word that we always found. Sometimes I find it a bit redundant because we always resort to numerical simulation. So when we talk about agent-based modeling, we talk about computational solutions, so numerical simulation of the model. So computational modeling of economics processes as open-ended dynamic system. We talk already about the open-endedness of complex system, in which we have interacting agents. So agent-based economics is at the crossroad, or you can say three different fields of research. So evolutionary economics, that I said has paved the way for the introduction of complexity in economics. Computer science, because, as I said, we use computational methods for agent-based modeling. And also cognitive science, because we model our system from the bottom up. As we will see, when we build an agent-based model, we first identify what are the rules of behavior of agents, what are the rules of interaction of agents, and in order to do that, we need to make assumptions of how agents process the information. So from this definition, we have a number of features that we can isolate. So first of all, agents are heterogeneous. If we have all identical agents, life wouldn't be so interesting. We have autonomy. So once the modeler defines the rules of behavior of agents and the rules of interaction among agents, no other intervention is should be done or is required. We have a network that is explicit, even in agent-based models that are not explicitly network model, we have interaction among agents. So for example, even in a model that is that doesn't have direct interactions, agents evolve, so there is indirect interaction. So anyway, a network is implicitly defined. More and more now we define explicit networks because we have computational methods. We have also data to somehow ground a network approach. So more and more now we define agent-based models and network models. Networks in which agents interact on a local level. So it's very difficult or because it's very unrealistic to observe agent-based models with complete networks. So normally we have incomplete. Due to the nonlinearities and the fact that the properties or the evolution of the system cannot be inferred from the evolution of the single agents or from looking at the single agents, as I said before, for complex systems, use heuristics. So we define agents normally as boundedly rational because the standard optimization is not applicable in agent-based models. All these elements lead to a dynamics that is a non-equilibrium dynamics. So with agent-based model very often generates ergodic series, but it doesn't mean that we have an equilibrium configuration in which all agents are happy, or agents, let's say, satisfy their objective function, and the system is in a steady state. So this is a possible outcome. It's not impossible, but it's not the natural evolution of the system, the final point of evolution of the system. So now I'm going to show you, I hope it works, a simulation of a simple model, which is the Schelling's segregation model. The segregation model seems to explain why agents tend to cluster. So the idea was that why in American cities, in US cities, we have clusters that are homogeneous from an ethnical point of view, despite people not having strong preference for living in a suburb where other people have the same ethnicity as the agent. So I hope you can see the screen. So here I'm using an external, so this is not my simulation. So Professor Magone provided that. So we have two types of agents that are the blue and the red. So we start with the situation completely random allocation of agents in each cell, and that's our starting point. Then we have a parameter that is let's say the behavioral rule of the agents, which is agents will be happy when at least, in this case, 30% of the neighbors are of the same color. Otherwise, agents will keep moving. So we have an initial situation, so an initial condition, which is basically randomly given. We have a behavioral rule, which is agents will keep moving until they are satisfied. And we have a parameter, in this case, a simple parameter, which is the homophily condition. So agents will be happy, so they will stop moving when at least 30% of the neighbors have the same color. So we can run simulation. So of course, we have a configuration. In this case, we have a Nash equilibrium because the system stops. Although, of course, it's enough that one agent changes to restart the whole dynamics. I would say we have a final point in which agents are clustered in blocks of the same color. Of course, if we restart, we will have a different outcome. So we have path dependency. So different initial conditions will lead to a different configuration. So in this case, I say we have a Nash equilibrium, but this Nash equilibrium is not unique. This Nash equilibrium changes depending on the path dependence of the path that the system goes through to arrive to this final. And of course, if we change the homophily condition, so if we rise this 30% to higher number, 50%, then we will have a stronger clusterization. So we see, in this case, the sensitivity to the parameter. So this is a very trivial example, but this trivial example allows us already to focus on the main characteristics. So as I said, the relevance of the initial conditions, the fact that we have a clusterization, even if agents are not strongly opposed to having neighbors of different colors. So they are happy with 30%, but still these generate clusterization. We have interactions because agents keep moving and their movement will trigger the movement of other agents. And we saw also how important parameters are. So this is probably the simplest example that we can observe of agent-based modeling, but we have already somehow all the elements there. So more practically, how do we think, conceive, and implement an agent-based model? So first of all, we need theoretical backgrounds. We need to conceive a virtual economy with different types of agents. Which type of theory do we adopt? Agent-based is, if you want, a technique. So it's not an economic theory. So it is agnostic with respect to the economic theory that basically underlines the model. But of course, since it is a technical tool, or if you want, a modeling approach rooted in complexity, it must be any theory that is employed should be compatible with a complexity approach. So we have, of course, discrete time because we need to make iteration in the simulation, and we have agents that are indexed in a discrete way. Once we define the economic model, which implies also defining the behavioral rules of agents, we need to assign parameters and initial conditions. We need to numerically give, numerical values, to parameters and initial. This is to test the validity of the model from an empirical point of view, or to mimic the behavior of a real economy. So there will be talks about estimation, so I don't talk too much about that, but there are different methods. So when we have data, we can of course use data. We can use optimization methods, and we can also introduce more recently a representation of the system. So basically a compact version of the model, a computational approximation of the model, which is called meta modeling, which is, if you want, a reduced form of the model made through computational techniques. So through these methods, we can estimate the parameters. Once we have the parameters, we have the initial condition, we can start simulating the model. So the simulation of the model implies that basically the only task of the modeler at this stage is simply to run the simulation. Once we have defined the model, we have defined the numbers within the model, then the model, through simulation, will generate dynamics. These dynamics, of course, depends on the behavioral rule and depends typically on idiosyncratic stochastic shocks. So in agent-based modeling, you don't typically observe big aggregate shocks in the SG models, but you observe idiosyncratic shocks that triggers the behavior of agents. So not all agents may be activated at every iteration of the model. some agents are activated, they are subject to idiosyncratic shocks. And these shocks and their behavioral rule will make them interact with other agents. At the end of each iteration, aggregate variables are calculated, and this calculation is simply the sum of the individual quantities. This creates, let's say, this changes the shape of the system. If you want, this is an avalanche that changes the shape of the system. So agents will incorporate in their informative set the new shape of the system, and this will lead to the next iteration in which agents with their own endowment and with their behavioral rules will react to the change in the system and will again determine the further evolution of themselves and the system. So and this is basically just a representation of all the three sets in a more, if you want, more formal way. Then the final part for the model is the analysis of the result. And in this case, the analysis is not so much different from the analysis of real data. We have a complete set because we have the data for all the agents, their evolution. So we can identify the emergent properties of the system. We can identify the dynamics, the variables that we want to study. So in this case, we can use any tool that is normally used in econometrics in order to identify and study what are the properties of the system. One thing that we can do with the agent-based model that we cannot do with real data is to study counterfactual scenario. So to study how the system reacts to changes in the parameters. So what we call the sensitivity analysis. So changes one parameter or groups of parameters at the same time. So now we can study, thanks to the evolution in computation, we can study the contemporary change, the effect of contemporary changes in all the parameters. We see how the system reacts. So we can test, for example, change in individual behavior or changes in policy, and we can test the effects of these particular changes in the system. So in macroeconomics, we have, so as I said, agent-based modeling started in the second part of the 90s. We have different schools that somehow took the lead in this pioneering period. Some of them are located in Italy. In particular, identify here three main, but of course there are more streams. One stream refers to the study of financial fragility in a Minskian perspective. So the study of basically how the financial system makes the macroeconomy unstable. And this is a field that is particularly suitable for the study of nonlinear and disequilibrium dynamics, in which agents are heterogeneous because, of course, some agents are net lenders, some agents are net borrowers, and in the aggregate, this compensate, but of course, this compensate until borrowers pay back. If they don't pay back, we have a situation of disequilibrium. So simulations of agent-based models have been quite interesting in highlighting some dynamics that with the standard DSG model couldn't be studied. As I say, the agent-based model is rooted in evolutionary economics. So evolutionary economists, of course, were on board or jump on board later on agent-based modeling. So we have a stream that is based in mostly the Sant'Anna School in Pisa in Italy. It's a class of Schumpeterian models, so model rooted in the Schumpeterian technological progress. Another school that is more rooted in industrial organization, so more focused on the study of industrial organization, is mostly based in Bielefeld in Germany. And then I wanted to mention a relatively new field, relatively new because it's the last, let's say, 5 to 10 years, but is mostly young, or now maybe not so young, researchers that have applied Keynesian models, so traditional Keynesian models, applied agent-based model in traditional Keynesian model. So Keynesian models are again suitable for agent-based modeling because in Keynes we have already somehow fallacy of composition, so we have already emergent properties. So, for example, the paradox of drift have that individual behaviors are the exact opposite of what we observe in the aggregate. So we have a situation that Keynes, of course, called the paradox, later on fallacy of composition, and now we can, using a complexity approach, we can call emergent properties, so dynamics that are not cannot be inferred by the single agent, by studying the single agent. So of course, so far I said I focus on the positive aspects, but of course there are issues that other economists have pointed out, or even within the agent-based community have been pointed out. First of all, and this goes back to the very beginning of agent-based modeling, so the fact that we computationally simulate the model means that we have a black box in which we have inputs, the model and the parameters, and we have outputs, but we don't know what's happening inside. This is something that probably applies less and less only to agent-based modeling because macro models today are huge, so they are normally simulated and causal chains are not always identifiable even in general equilibrium models. In the agent-based camp, one way to study causal relationship has been meta-modeling. So as I said, the identification of a representation of the model that approximates the original model, but also allows for a deeper study of the causal relationships through changes in the parameters. The second point that was stressed by Duncan Foley a few years back, so Duncan Foley was an early proponent of agent-based modeling. So his point is, okay, of course we reject variation equilibrium because, as we say, general equilibrium is only one of the possible outcomes here. But this basically, the equilibrium for economists should act as a discipline device, so should make models comparable and should avoid the trap of so-called anything goes. So anything that happens in the model is okay because we don't expect it. So how can we somehow rein in and have a discipline device for which we can compare models and we can identify what are the main characteristics of the model. So Duncan Foley proposes statistical physics, and in particular the idea of statistical equilibrium to replace the traditional notion of general equilibrium. And in order to study statistical equilibrium, we need sort of what we call a statistical mechanics. So I say that physics was basically the grandfather of Newtonian physics was the grandfather of the general equilibrium approach. So maybe we can go back to the new physics, or the physics that emerged from the quantum revolution in the 20s, and apply statistical mechanics. And Duncan Foley was a few years back one of the early proponents of this approach that was refined by Masanao Aoki in a series of books in which really he proposed a new way of modeling macroeconomics that is rooted in statistical mechanics. Myself, with my PhD supervisor and Mauro Gallegati and Simone Landini, who is a mathematician in Italy, we basically use Aoki's approach to try to define a closed model, so to find the statistical equilibrium. But of course, here the field is still quite new, and so new developments should be done in order to talk to other economists. So I want to close basically to say paving the way for the future, for the discussions of today. As I said, we have a complexity approach to economics that is somehow interesting, or can say something more with respect to the general equilibrium. This implementation generates problems. We saw some way to overcome this problem, and we will see today all the developments that from this general idea in the 90s have led to what is agent-based modeling today. So maybe this idea of this question of is agent-based modeling a mature field can be in the background of our mind today while we listen to the other interventions. And we will see, for example, application in networks, so with a more explicit network theory behind the implicit network that is already defined in agent-based modeling. We will see we will listen to two experts on estimation of agent-based modeling. Estimation, let me say, is not a problem only of agent-based modeling, because any large model has trouble in estimation. So we have last year there were a number of papers coming out and somehow criticizing how DSG models are estimated. It's not surprising that from agent-based modeling, we can talk to experimental economists because the underlying dynamics is the same. So the study of how individual agents make decision and how the decision somehow interconnect with each other. And finally, agent-based modeling is very apt for the study of distributional issues because, of course, we have the possibility of having agents that are fully heterogeneous in all the possible dimensions. And I would stop here, so I didn't keep track of the time. So